Okay, good afternoon. Welcome to this Dublin lecture. The Wolfgang Dublin Prize from Plenary Society was established in 2011 to honor the scientific work of Dublin. It is awarded biannually to a single individual for outstanding research in the field of probability and who is at the beginning of his or her mathematical career. The prize is generously supported by the Springer. The 2018 Dublin Prize recipient is Jason Miller. Although Jason is only 8 years after his PhD, he has already made some amazing contributions in probability theory. Jason, in fact, one can find some trace. I just found out today that Jason majored in 3 areas in college from University of Michigan. He majored in mathematics, computer science, and economics. He got a PhD from Stanford University in 2011, and then he did a postdoc at MSRI, at Microsoft Research from 2010 to 2011, then postdoc at MIT from 2012 to 2015. He moved to Cambridge University in 2015, and where he is now a reader. Jason's research interest is in stochastic interface model, including Gaussian free field, random work on random planar maps, and SLE. Among his honors, he received Lola Davidson Prize in 2015, Whitehead Prize in 2016, Clay Research Award in 2017, and he was an invited speaker at ICM 2018. And then he received this Dublin also prize in 2018. Now, the citation of this prize is the following. Jason Miller is an outstanding mathematician who has an impressive collection of deep results in probability theory. He has made fundamental contributions to the study of two-dimensional random geometry and the related aspects of mathematical physics and conformal geometry, combining ideas from several areas, including combinatorics and stochastic analysis. Particularly noteworthy are his work on imaginary geometry, Liouville's quantum gravity, and the scaling limits of self-avoiding works, and the critical percolations on random planar maps. So now I invite Jason to come forward to receive the certificate and then give this Dublin's lecture.
Okay, so first of all, I want to say that I'm very happy and honored to be here today. So what I'm going to be talking about is based on work that I've done in collaboration with Ewan Gwynn, who is currently also based in Cambridge. And just to start to put what I'm going to say into better context, I want to begin kind of slowly by reminding you that in two-dimensional probability, there are a number of very important canonical objects. So the most basic one is Brownian motion, and you can think of this in some sense as the canonical model for a random continuous curve. There's the Schramm-Loewner evolution, and you can think of Schramm-Loewner evolution as the canonical model for a random continuous curve with the additional constraint that it's not allowed to cross itself. Another very important example is the continuum random tree, which is a canonical model for a random planar tree. And what I'm going to be talking about today is something called Liouville quantum gravity. And one way of thinking about this is that this is a canonical model for a random surface. And so I'm going to spend a little bit of time in the beginning talking about where this comes from and why you would want to study it. And then I'll talk about some of the results that we've proved recently. And I should mention that of these 4 pictures, I only made 3 of them. And so the last 3 pictures were made by Tom Kennedy, Igor Korchemsky, and Jeremy Bettinelli. Okay, so I'm going to begin by talking about what Liouville quantum gravity is. And again, this is supposed to be a model for picking a two-dimensional manifold at random. And you could ask yourself, what might be the right way to do this? And luckily, this is a question that was considered by somebody in the physics literature, Polyakov, back in the 1980s. And what he said is that the right object to look at is the random metric that you get by taking the Euclidean metric in 2 dimensions, and you perturb it by the factor e to the gamma h, where gamma is a parameter which can be between 0 and 2, and this h is an instance of the Gaussian free field. So the parameter gamma, this dictates how rough your surface is, and so when gamma is equal to 0, it just corresponds to a metric on a planar domain, and for larger values of gamma, you get something which fluctuates more and more wildly. So just to remind you, the Gaussian free field is the Gaussian random field on a domain D, and the covariance function, G, is given by the Green's function for the Laplacian on your domain. And the important thing here is that the leading order behavior of this Green's function is given by the log of the distance between your 2 points. And the Gaussian free field's a very important object in probability in 2 dimensions because it has lots of very useful properties. In particular, it's a conformally invariant field. It's Markovian. And actually, it's in some sense a 2-time dimensional analog of Brownian bridge. Now, there's kind of a problem here in the definition of Liouville quantum gravity because the free field in 2 dimensions actually isn't a function, and so you can't exponentiate it. Rather, it's a random variable which takes values in the space of distributions. And the reason for this is that this covariance function, this actually blows up to plus infinity as x approaches y, and so the random field that you have has infinite variance at points. And so what this means is that, again, this expression doesn't really make sense mathematically, and it requires some kind of interpretation. But it's a very interesting object to look at because it has connections with many different things in probability. So it's deeply connected to actually all of the other things I mentioned on the first slide and a number of other things. And one particular connection and motivation for wanting to study Liouville quantum gravity is something I'm going to talk about even more. And this is something which on the surface looks quite different, and this is the theory of random planar maps. So just to remind you, what is a planar map? So this is a graph with an embedding in the plane so that no 2 edges cross. So it could look something like this. And if you think about it, for a couple of minutes, you'll realize that when you fix the number of faces in a planar map, there are only a finite number of possibilities, and so you can talk about picking one at random. And that's what a random planar map is. And one particular nice way to think of constructing a planar map is the following simple procedure. So you can imagine that you have a piece of paper, and then you just get out your pen and your ruler, and then you take your piece of paper and you divide it into a bunch of squares which have equal size. And then you get out your scissors and you cut this into actual individual copies of the unit square. And then you get out your bottle of glue and you glue it together. And you do this in some way so that what you get is topologically, let's say, a 2-dimensional sphere. Okay? And if you've done it properly, you'll get something which looks something like this piece of origami here. Okay, so this is what a random quadrangulation is, and this is how you can sort of think of this as also corresponding to a type of surface. Now, quadrangulations with 12 faces are not perhaps the most interesting objects to analyze. They get a lot more interesting when the number of faces is large. And so here's another picture which has 25,000 faces. And then this random surface was embedded into 3-dimensional space. Now, the embedding that you have here is actually not even close to being an isometry. But I think these kinds of pictures are very useful to look at because they remind us that when you think about random surfaces, just like when you think about most models for random curves, you're going to get something which is very rough and fractal. Okay, so there were these conjectures that were sort of floating around, going back to the 1980s, very soon after Polyakov's original papers. And they said that this construction, Liouville quantum gravity, this was supposed to be the right continuous object to look at if you wanted to mathematically describe the large-scale behavior of many different types of these random planar map models. And here you have this parameter gamma again that you're allowed to change. And how you choose gamma, this sort of dictates what type of random planar map model you're supposed to be looking at. So for example, when you take gamma to be the square root of 8/3, then this corresponds to a planar map chosen uniformly at random. And other values of gamma, they correspond to what happens when you have some extra structure. So for example, when gamma is the square root of 2, then this corresponds to a planar map with the extra structure of a spanning tree. The reason that the value of gamma changes is that you actually change the law that you use to pick your planar map model. So it's biased by the number of spanning trees that you have on your graph. And when gamma is the square root of 3, it corresponds to a planar map with the extra structure of the Ising model. And actually, for every value of gamma between 0 and 2, there's a very natural model from statistical mechanics that you can put on top of your random planar map, and you will get that type of Liouville quantum gravity. And there are lots of works now that have proved these types of statements, but in each one of these papers, they always require interpretation because, on the surface, we're talking about two very different objects. So on the one hand, we have random planar maps. These are something which is very concrete. This is just a random graph. And Liouville quantum gravity, on the other hand, is something which a priori does not make mathematical sense. And so what you have to do when you prove a statement of this type is you have to think of some way of making sense of this, and then proving that the corresponding planar map model converges to that object in an appropriate topology. And so what I'm going to talk about today is the question of how you put a metric space structure on Liouville quantum gravity, or a distance function. And this particular question is something which is very natural in view of this connection with random planar maps, because the natural structure that you have on a planar map, which is a graph, is just its distance function. And so you want to be able to have a distance here in the continuum. It's also natural because this is supposed to be a random Riemannian manifold, and one of the most fundamental objects that you have on a Riemannian manifold is its metric. So before I go into that, I want to spend just a couple of more minutes talking about why people are actually interested in these types of connections between planar maps and Liouville quantum gravity. And this comes from questions which a priori look very different. And one of them is related to something called the Brownian intersection exponents. And what this concerns is if you have this, say, Brownian motion in 2 dimensions, then there are lots of very interesting questions that you can ask about the fractal properties of the Brownian motion. And one of the most famous conjectures which was around is that the Hausdorff dimension of the outer boundary of the Brownian motion is 4/3. So this was a conjecture made by Mandelbrot. And for this particular property of Brownian motion and many other interesting fractal properties like the dimension of its cut points, you're sort of led to try to calculate a certain probability. And this is what's referred to as the Brownian intersection exponents. And what you do is you imagine you have a little disk, let's say of radius epsilon, and you start a certain number of Brownian motions, like for example, it could be 3. And then the question that you ask is, what is the probability that these independently chosen Brownian motions actually make it to the boundary of this disk without intersecting? And it turns out that this is actually a very difficult question to analyze. And I want to just explain to you now the story of this and how it's connected with planar maps. So the the sort of history is that people working in the physics literature, like for example, Bertrand Duplantier, who's right here, they realized a long time ago that questions of this type are actually a lot easier to analyze when you work on a random surface like this, rather than in the plane. And the reason for this is something which makes a lot of sense. The sort of idea is that if the underlying geometry is random, then you have to keep track of a lot less information when you're exploring your, let's say, your Brownian paths or a percolation interface, etc. And it sort of has the effect of converting very complicated, geometric questions to questions that can actually be rephrased in terms of, sort of classical things about stochastic processes in one dimension. And so what happened is that Duplantier, he formulated and solved this question, at least in the physics sense, in the context of a quadrangulation. And when you do the calculation in that setting, you're actually going to get different exponents because you're working on a different type of geometry. But people working in physics, they sort of realized what the right way was to convert exponents you would calculate on a random geometry to a deterministic one. And this is something called the KPZ relation. And so this is, again, a non-rigorous step that somebody in physics would perform. But when you combine these two steps together, you have a prediction that you can then try to prove mathematically. And then what happened is that Lawler, Schramm, and Werner, in one of the very early papers, really spectacular successes at SLE, proved that the formula derived in the physics literature was actually correct. And there are many other examples like this, where the behavior of some type of critical model was predicted by first analyzing it on a random surface and then applying this KPZ formula. And so one of the reasons people like to work in this topic is that one of the sort of ultimate aims is to put these types of methods onto more firm mathematical ground. Okay, so that's a bit of motivation. Now let me turn and start to talk about the question of how one makes sense of Liouville quantum gravity. So there are two, or at least two, sort of very important things that you have with every Riemannian manifold. So you always have a volume form, so some way of measuring areas, and you have a distance function. And as sort of a warm-up for talking about the distance function, I'm first going to tell you a little bit about how one makes sense of the area measure for Liouville quantum gravity. And okay, so again, what you're doing is you're looking at this random metric here. And the problem is always that you're exponentiating the Gaussian free field, which is a distribution. And whenever you're presented with this kind of problem, there's something which is very natural to do, which is you take your distribution, you choose some way of mollifying it, and then try to take a limit. And in this case, there's a very natural way to mollify the Gaussian free field. You can take it and you can compute its averages on boundaries of balls of radius epsilons. You can consider what's called the circle average. And then you get a nice continuous function, and there's no problem exponentiating that, and then you can take a limit as epsilon goes to 0 of these random area measures. Now when you do this, you have to be a little bit careful, because there's a bit of a problem, and that's that the fields that you have here, these h epsilons, they're going to be blowing up to plus and minus infinity, because the variance of the Gaussian free field averaged at a circle of radius epsilon turns out to be have leading order log 1 over epsilon. So to fix that, you have to put this extra term here, epsilon to the gamma squared over 2, because this is exactly what you need to have so that if you were to take an expectation of this, then you would get something which is not blowing up as epsilon goes to 0. And this type of construction has actually appeared in lots of different places. The very first one that I know of is a work of Hoek-Kroon back in the 1970s. There's also a theory of what's called Gaussian multiplicative chaos, which was developed by Kahan back in the 1980s, where they're exactly looking at measures of this type. And then there's this paper which was due to Duplantier and Sheffield, And this appeared on the archive back in 2008, but I think actually they were giving talks about this several years before it went up on the archive. And one of the reasons that this particular paper here is very important is that this is one of the things that really kicked off the study of these objects within the probability community. Okay, so that's how one constructs the volume form or the area measure. And now I'm going to talk about the distance function or the metric. Now, prior to these works together with Ewan, the metric for Liouville quantum gravity was built in one special case, just when gamma is the square root of 8/3. This one, again, just to remind you, is what corresponds to planar maps chosen uniformly at random. And the construction in this case was actually something which was very indirect. So somehow what was done is we sort of built a growth model, sort of a growing family of sets, which turned out to correspond to metric balls in a metric space using Schramm's SLE curves. And this worked, but perhaps a more natural way to try to build a metric is just to repeat what was done in the case of the volume form. And to do that, again, what you do is you're going to take your Gaussian free field, you're going to mollify it in some way. Once you do that, you have a very natural notion of distance, which just comes from the surface which corresponds to the mollified field. And these approximations have been the subject of several works, which I'll talk about in just a moment, and they have a name. They're called Liouville first passage percolation, because they're related to the first passage percolation model. Now, one thing that I want to take a moment to emphasize is that here inside of this exponential, you see this number psi, and psi is not the same thing as the number gamma, which was used to build the volume form. Rather, it's given by gamma divided by something else, which is called d sub gamma. And d sub gamma is an exponent, which was constructed by Jian Ding and Yuan Guin, and it describes the growth of volumes of metric balls. So what this means is that if this were a metric ball inside of this space, so not the Euclidean metric, but the random metric, and if it has radius epsilon, then it should be true that the volume of this ball behaves like epsilon to this number d sub gamma as epsilon goes to 0. Now, of course, when they constructed this, there wasn't a Liouville quantum gravity metric to work with, and so they somehow constructed this from the perspective of different types of approximation schemes, and they showed that this thing exists. And sort of after the fact, this will actually correspond to the growth of balls in this space. Okay, so now I want to explain why you see psi here and not gamma. And the reason is basically it comes from scaling considerations. And you have to understand what happens to different quantities when you take your field and you add a constant to it. So we can look at what happens to volume, and we can also look at what happens to area. Now, in terms of distance, what happens for distances, if you add a constant c to your field, that's just going to correspond to adding a constant c up here, and this will multiply distances by the factor e to the psi c. So under the metric, after adding the constant, this ball of radius epsilon will become a ball of radius epsilon times e to the psi c. And therefore, its volume should be something like epsilon times e to the psi c, all to this power d sub gamma. On the other hand, from the way that the measure is constructed for Liouville quantum gravity, when you add a constant c to your field, it has the effect of multiplying volumes or areas by the factor e to the gamma c. And so from this perspective, you know that the volume of this ball under the new metric is going to be epsilon to the d gamma times e to the gamma c. And therefore, these two things have to be the same. And so you get this identity. And if you just solve for what psi has to be here, you see that psi must be gamma over d sub gamma. And so you get something different from gamma. OK, so now I want to tell you about some of the results that were proved previously for these types of approximations. So there are a number of works which looked at the question of showing that these objects are actually tight. They define a tight family of metrics when epsilon goes to 0. So the very first work of this type was from John Ding and Alex Dunlap. And what they showed is that these approximations are tight, but they showed it only for values of gamma which are extremely small. Okay? Then there was a more recent work by Julien Dubedat and Hugo Falconet, where they also proved tightness, again for small values of gamma, but the sort of improvement was that the range of gamma values that they considered was a more explicit range of small gamma values. And they also had some other sort of very nice features of the argument that were new. And then very recently, this was actually, I think just back in December, there was another paper by Ding and Dunlap, and they managed to prove tightness for the entire range of values of gamma between 0 and 2. The difference was that they actually proved this for a slightly different model called Liouville graph distance. So this is another way of thinking of approximating a metric, which is very natural for certain perspectives. And they showed that for these approximations, which I'm not going to define, you again have tightness. And then these two teams, so Ding and Dunlap and Dubedat and Falconet, they teamed up. And just very recently, I think this was 2 months ago, they posted a paper where for the LFPP approximations, so for this model again, you have tightness for the full range of gamma values between 0 and 2. And this was something which was very nice for us because this model has certain special features which make it easier to prove lots of different things about it. OK, so now let me take a moment to show you a picture. So this is a picture of what a metric ball looks like in Liouville first passage percolation. So here I've taken the value of gamma to be equal to the square root of 8/3, just coincidentally. And then on top of the metric ball that you see here, where the colors represent different radii, I've drawn geodesics. And the geodesics start from a grid of points inside of the ball, and they're all going back to the center. And one of the very important things that you see in this picture, which is very important for the analysis, is the confluence of geodesics phenomenon, which says that if you take two geodesics started at different points, let's say here and here, then as they travel back to the center of the ball, they're going to eventually coalesce. Okay? So this is something which is actually exactly the same or analogous to what Alan was talking about in his talk, but in a different context. And I'll say a few more words about this later on. So one thing which kind of disturbed me a little bit is I was making lots of pictures like this, and I sort of noticed that for different values of gamma, the picture that you get somehow always looked basically the same, at least when you do it in the sort of range of gamma values which is most physically interesting, which is when gamma is between the square root of 2 and 2. And there's a good reason for this, which I want to just take a moment to explain. And that's that if you look at the plot of the exponent that you put in there, so gamma over d sub gamma, then once you make it over to this range where gamma is between the square root of 2 and 2, it looks basically flat. So when gamma is the square root of 8/3, it's about 0.41. It's also about 0.41. Gamma is the square root of 3. And it only differs by about 0.02 once you go down to the square root of 2. So the pictures that you get don't really look that different, even though they do describe different objects. Now, one other thing I want to emphasize is that this volume growth exponent, d sub gamma, which was constructed by Ding and Nguyen, it's actually not known what it's supposed to be. So their construction is somehow indirect. It's just building an exponent. We, in fact, only know it for square root of 8/3 when it's equal to 4. But for other values of gamma, we don't know it. And but in one of the in the work of Ding and Gwyn, they proved very precise bounds for what d sub gamma is. And so this plot that I've generated here is perhaps not exactly correct, but it's very close to the true value of psi as a function of gamma. Okay, and so now let me just state what our main theorem is. So the theorem is that if you look at the LFPP approximations, so d sub h epsilon, then the first sort of part of the result is that they don't just converge along subsequences, they actually converge in probability as epsilon goes to 0 to a limiting metric, d sub h. And this d sub h has a number of important properties. So it turns out that it's singled out by a couple of things. Namely, it turns out that it's locally determined by the Gaussian free field. It defines a metric which is homeomorphic to Euclidean space, and it also plays well with conformal maps. And this is this characterization is something which is actually quite important in the proof. And so I'm going to say a couple of more words about this later in the talk. And then the last thing I wanted to mention is that when gamma is the square root of 8/3, this gives you a metric which is exactly the same as was constructed previously in the work with Scott Sheffield. So it's a very different construction, but it gives you exactly the same object. Okay, so in the last part of the talk, what I'm going to do is I'm going to describe to you some of the ideas that go into proving this result. Before I do that, there's one other thing I'm going to do first, which is I want to discuss a little bit further how this is related to the previous work when gamma is the square root of 8/3. So the construction from before, again, this was somehow done by trying to make sense of a kind of growing family of sets, which turned out to be metric balls in a metric space. It's a kind of version of the Eden model built out of SLE6. And the previous argument, it really hinged on very special properties that you have with SLE6 and Liouville quantum gravity when gamma is the square root of 8/3. So what happens when you consider these two objects together is you see lots of different exact formulas coming out because these objects are closely corresponding to certain types of Levy processes. And so you can do lots of computations. And this was something which was also very important in this proof, because this is really what made it possible to show that the metric when gamma is the square root of 8/3 is the same thing as the Brownian map, the scaling limit of uniformly random planar maps. But when gamma is between 0 and 2, in this more general context, the argument is very different in the sense that it makes actually no use of the Schramm-Loeffner evolution. And one of the consequences of that is that we actually don't have any exact formulas for anything at all. And somehow the way that the proof works is that it's based on more elementary Gaussian free field techniques rather than magic that comes from SLE. And the starting point for the construction is a definition. It's something that we call a Liouville quantum gravity metric. And what this is it's just a minimal list of properties that any metric with Liouville quantum gravity would have to satisfy. One other sort of big difference with the previous work is that we're trying to build a particular random metric space, and you don't have some other construction which came beforehand from a different perspective. So when gamma is the square root of 8/3, you have this object, the Brownian map. It's very easy to describe what it is, and because of this explicit description, you can do lots of computations. And so you sort of know, what you're aiming at in that setting. But for general values of gamma, we're sort of building the object in question, and so you don't know what properties it's going to have before you've made sense of it. At the same time, I'm not trying to make a claim that this supersedes the previous work that was done when gamma is the square root of 8/3, because the connection with SLE is extremely important for making connections to planar maps, or in this case, the Brownian map. So in general, you only see exact formulas coming out or special properties of different values of gamma when you use SLE. And from the other perspective, nothing is a priori special at all about, for example, gamma equal to the square root of 8/3. All right. So what I want to do is I want to explain what the definition is of a Liouville quantum gravity metric. And one of the important parts from it in the definition comes from the coordinate change formula in Liouville quantum gravity. So let me remind you that you have this random measure, which is defined by taking the exponential of the Gaussian free field, properly renormalized. And when you apply this renormalization, you have this factor epsilon to the gamma squared over 2. It has sort of this effect that you get a different change of coordinates formula than you have in usual calculus. So you have a modified version of it. And the way that it works is, let's suppose that you have a domain D, like this guy, and you have your Gaussian free field, which is defined on D. Then you can always build this, this measure. And then you want to see what happens when you take your domain and you map it to another domain. Now, if you want the measures to play well with the conformal transformation, then when you build your measure in the domain d tilde, you have to add a correction. And this correction is given by the log of the derivative of your conformal map times this number q. So q is 2 over gamma plus gamma over 2. If this term was not there, then q would just correspond to 2 over gamma, and you wouldn't have this term. Where this term comes from is the epsilon to the gamma squared over 2. Okay, so this is just a modification of the change of variables formula, which works in this setting. Okay, so now with that in mind, I'm going to give you the definition of what we call a Liouville quantum gravity metric. And it's a little bit easier if you assume that you're working on the whole plane, because then you have fewer conformal maps and extra nice properties to work with. So we're going to call a metric a Liouville quantum gravity metric if it's coupled with the Gaussian free field. It defines something which is homeomorphic to Euclidean space, and it satisfies a couple of extra axioms. The first axiom is that it should be a length space. So this means that if you have 2 points inside of the z and w, inside of the complex plane, then you should always be able to find a path connecting them whose length is at most their distance, the distance between z and w plus the number epsilon. So this is a very natural property. The next axiom is the assumption of locality. And what this means is if you have an open subset inside of the complex plane, then you can always build the internal metric associated with d sub h on U. And it should be true that this metric is a function of the Gaussian free field values on the set U. So this says that somehow distances are locally determined. The next important property is what's called Weyl scaling. And what this says is that if you take your metric and you consider what happens when you add the constant c to your field, then this should just have the effect of multiplying distances by e to the psi c. Okay? And something else, the same thing should hold if you consider what happens when you add, let's say, a continuous function to your field. And the last property is that it should be compatible with coordinate changes in exactly the same way that the construction of the measure is compatible with coordinate changes. And what this translates into is this identity here, which again just says that the metric satisfies the same coordinate change formula that the measure satisfies. Okay? And it's going to turn out that this is all that's going to matter. So you just have these properties, and there's exactly one object which satisfies these properties. So this definition, it's actually equivalent to an earlier definition, which came in a work that I wrote with Wei Qian. And we were looking at a very different question. So we were trying to understand, how are geodesics in Liouville quantum gravity related to the Schramm-Loven revolution? It turns out that they're not related at all. They're completely different. And at the time, there was only a metric constructed when gamma is the square root of 8/3. So we were just looking at that setting. But when we tried to analyze this question, we sort of realized that we didn't want to use any of the special properties when gamma is the square root of 8/3. Things seemed to work if you just looked at a more general framework. And we wrote down a definition which is equivalent to this one that you see here. And kind of the way that this part of the project developed is at the same time I was talking to Ewan quite a lot. And then he went off and he came back shortly, maybe 2 months later, and he produced an enormous number of very useful estimates, also just assuming these properties, which eventually went into this proof. Okay, so this is the definition of a Liouville quantum gravity metric. What I want to do is I want to try to describe, just in 2 slides, what the sort of ideas are that go into showing there's, number 1, at most 1 Liouville quantum gravity metric, and number 2, that one actually exists. So the first thing that we sort of realized is that if you assume you have 2 Liouville quantum gravity metrics, so remember we want to show that these things are eventually the same, we realized that it's actually surprisingly easy to show that they have to be bi-Lipschitz equivalent. In particular, you can find 2 deterministic constants, C1 and C2, so that the metrics that you have are bi-Lipschitz equivalent. And once we sort of realize that, then you sort of know exactly what you want to do. Namely, you want to show that for these 2 metrics, these 2 constants have to be exactly the same. And so the rest of the proof is aimed at verifying this equality. And it has a couple of steps which go into it. The first important step is proving the confluence of geodesics phenomenon. So again, what this says is that if you have 3 points, let's say the origin Z and W, then it should be true that the geodesic from Z to the origin should agree with a segment of the geodesic from W to the origin. So they should eventually merge. And this is something which is very useful. The reason that it's useful in this particular context is that what it tells you is that if you look at a geodesic in Liouville quantum gravity, then the local behavior of the geodesic in different places is going to be approximately independent. The reason that this is kind of a non-trivial statement is that geodesics are not local functions of your field. To know that this is a geodesic, you kind of have to know the entire field that you're looking at here. Okay? So even though the Gaussian free field satisfies very strong independence properties, it's not obvious that it translates into geodesics, and this is what confluence of geodesics translates into. And the reason for this is that you could kind of imagine resampling the values of the Gaussian free field in here, and the reason that this is not going to move the entire geodesic around is that there are going to be a lot of other geodesics sort of nearby, which will be merging into this long geodesic. And so this is something which had been proved previously in the context of the Brownian map by Le Gall, and it's something which is actually also quite important in the context of proving that the Brownian map with the scaling limit of uniformly random planar maps. But the proof of this is somehow very different than Le Gall's proof, because in the context of the Brownian map, you see lots of familiar stochastic processes. And so therefore, you can do lots of calculations, and you can see that you have the confluence of geodesics phenomenon as a consequence of properties of certain stochastic processes. Whereas in the setting of the Liouville quantum gravity metric, we're just assuming that we have something which satisfies these properties, and then we want to show that, assuming that, it must be true that that geodesics actually do this. Okay, now the next kind of step in the proof is to argue by contradiction. So we assume that we have the optimal by Lipschitz constants associated with our two metrics. And our goal is to show that these two constants are actually the same. And the way that we did this is we did it by contradiction. So we assume that actually C1 is not equal to C2. So C1 is smaller than C2. And the way that the contradiction argument works is we try to show that if that were true, then C1 and C2 could not have been optimal. And sort of the way that the argument works is that if it's true that C1 is not equal to C2, then there have to be lots of places where you have paths where the ratio is bounded away from C1 and C2. And you want to show that somehow these sort of shortcuts actually have to appear all over your geodesic. And then the last part of the proof, the final step, is to extend the definition to domains which are not necessarily the same as the complex plane. So using the Markov property of the Gaussian free field, it's actually fairly easy to construct a metric which is defined on domains which are distinct from the whole plane. The part which is actually surprisingly was a little bit tricky for us was to show that this metric actually is conformally covariant. So it satisfies the same coordinate change formula which is satisfied by the measure in Liouville quantum gravity. And so these are the 4 steps, and each of these steps is carried out in one of 4 papers. So this is the proof that there's at most one metric for Liouville quantum gravity. Then you want to show that a metric actually exists, and this is where Liouville first passage percolation comes back into the picture. So if you take a subsequential limit of Liouville first passage percolation, you're going to get something which is obviously a length space because you're taking a limit of something which is a length space. It's going to satisfy the Weyl scaling property, which tells you how distances change when you add a constant to the field. And if you define it out of the whole plane Gaussian free field, then it's also going to be translation invariant because the approximations are translation invariant. And so the non-trivial things that you have to check are that the metric that you have is actually locally determined by the Gaussian free field. And the other sort of key thing is showing that it defines a metric which is scale invariant. So it works with the Liouville quantum gravity coordinate change formula in the whole plane. And let me just mention that the way that the first part works is it's kind of an Efron-Stein style argument where you want to show something like the conditional variance of the metric that you're constructing is equal to 0 and therefore determined by the Gaussian free field. I don't want to go into too much detail about that. And the second part is that this characterization of Liouville quantum gravity metrics actually does not require exact scale invariance. So you don't have to assume that you're working with a scale invariant object to show that you have at most one, and therefore you can use this to prove scale invariance. And the proof works with an approximate form of scale invariance. So you don't have to read what this actually says, but basically this is the sort of approximate form of scale invariance that you get by virtue of the fact that you're just working with a subsequential a limit, something which is tight. And this sort of set of ideas is developed in another paper, which is by Julian Dubada, Hugo Falconet, Ewan Gwynn, Josh Pfeffer, and Xin Sun. And so once you have that, then you can feed this into the same characterization argument to say that you actually have a metric which is also scale invariant. Okay, so that's sort of summarizes all of the ideas which went into the proof of this result. Let me now finish in these last few minutes by mentioning some further questions that we're interested in. So the first one is, can we do something like this in higher dimensions? So, might there be an argument which works, say, in 4 dimensions or 3 dimensions? And the proof actually only makes use of planarity in a couple of spots. So number one, in the proof of tightness, there are some RSW type arguments, which come in and are quite important. And also the argument for the confluence of geodesics also relies on planarity. And so it's natural to wonder, is it true or is it not true that you have confluence of geodesics in higher dimensions? And this is something that we don't know the answer to. It could be that once you go to a high enough dimension, or maybe even 4 dimensions, geodesics just don't see each other anymore. And if that were the case, then you wouldn't have confluence. But maybe it's still true. And we don't know if there's a strategy for proving tightness which doesn't use these types of RSW type arguments. So at this point, we only know that the square root 8/3 Liouville quantum gravity metric arises as a metric space scaling limit of random planar maps. But now that we have this metric for all gamma, you can ask whether or not, for general values of gamma, it arises as a metric space scaling limit of random planar maps. And one particular case that would be quite interesting, for example, is when gamma is the square root of 2. So this is the object which corresponds to planar maps with the extra structure of a spanning tree. So now we have the limiting object, but the sort of major mathematical challenge is that the way that these planar maps are analyzed is by using certain bijections. And the bijections for planar maps, which are not chosen uniformly at random, somehow don't tell you anything about distances. And that's what you need if you want to prove a metric space scaling limit. Also, we don't know what the value of this function is, d sub gamma, which gives you the volume growth exponent, except when gamma is the square root of 8/3. It was shown after the fact by Gwynn and Pfeffer that this actually does give you the Hausdorff dimension of the metric, but we don't know what the number is. There are different predictions as to what it's supposed to be. So there's one from the physics literature going back to the 90s due to Wadabiki, and he said, maybe maybe d sub gamma is given by this function here. And this did for a long time, until relatively recently, Jianding and Subhajit Goswami showed that this prediction is actually wrong when gamma is small. And now there's another prediction, which I'm calling the Gwynn prediction. So this is due to Ewan, and he's guessed that perhaps the function d sub gamma is given by this formula here. And this one is consistent with all known bounds, and so maybe this is actually the correct answer. It would be a lot nicer because somehow all of the formulas in the subject turn out to be quadratic, and this one's also quadratic, so that would be something which would be particularly convenient. The other thing that we've been wondering about is that because this construction is kind of indirect, we don't have exact formulas for anything. This is, again, in contrast to the square root 8/3 case, where you can write down exact formulas for lots of different things, because of the relationship to the Brownian map. And the kind of final question is, there's the critical value of gamma where it's actually equal to 2. So when gamma is equal to 2, you can construct a measure for Liouville quantum gravity. It's a little bit more delicate than constructing it when gamma is smaller than 2. And so there should also be a metric in this case. The case gamma equals 2 is also physically interesting because it would correspond to a planar map with the extra structure of the Potts model with 4 states. But at the moment, this is something that we don't know how to extend the proof to. Okay, and that's all that I wanted to say, and so I'll stop there. Oh, so this problem, again, this was something which was solved by Lawler, Schramm, and Werner about 15 or 18 years ago. Yeah, so this was something which people predicted in the physics literature using these types of techniques, and then mathematicians, in particular Lawler, Schramm, and Werner, proved it using Schramm-Lovener evolution.
Just for the record, it was predicted before
I was hoping that you would not mention that. So there is an earlier, I like this example because it's sort of the nicest one to explain, but as Greg mentioned, there's also an earlier paper by Duplantier and Quan, so you at least have overlap of one co-author, which did it using different techniques.
Let's thank Jason again for this.